Okay, welcome to Design of a Level 2 High Power Rocket, Part 2. This one is going to focus on material structure and construction. So the first thing before we kind of get into like actually building stuff is understanding the actual forces that are on the rocket. And one of the things that I kind of like to do is dividing up L2s into kind of like two groups. And this isn't like anything that's super empirical, and you can easily build something that's in between them. I think it's helpful to think about it in terms of this. Um, you have both the smaller L2s, which kind of tend to be very large L1s, um, 5 feet tall or so, and on a smaller L2 motor, they could fly to easily 3,000 feet. Um, on the larger side, uh, think more Battle of the Rockets or USLI for those born after 2000. Um, that's more like 8 feet plus tall. And on a small L2 motor, those will only get to around 1,000 feet or in between that and 2,000 or so. And I think when you're starting to design your L2 rocket, I think it's helpful to try and think about what kind of you're going for. Depending on what launch sites you are able to go to, um, you know, if you have a place with a really low waiver, you might consider building a larger L2 so that you fly under that. Um, I personally, I think the trend has been in the past, more people built these like large L2s, although, you know, with my year in particular, me and Thierry, and I don't, I think Chris too, have all started building these smaller L2s. And part of the advantage with that is I personally think they look cooler, although that's very subjective. But smaller is cheaper in general, and it can be easier to manage. Um, Onto actual forces, though, you'll notice I have a nice screenshot from Troy's FEA workshop. I very highly recommend that if you haven't seen that, you go watch it. Um, it's a great way of actually understanding this. Um, but one of the very important things is that you consider how forces are transferred through parts and ultimately into the airframe. Um, any force that is exerted on a small part of your rocket eventually has to be transferred to the rocket as a whole. Um, and you have to keep in mind that, you know, you can have the strongest part, like aluminum bulkhead, whatever, but that doesn't mean much if it's affixed to something that's not strong enough. Uh, like, putting a wooden aluminum airframe, or sorry, aluminum bulkhead and affixing that inside a phenolic airframe, that's a good way to break something. Um, and these are all concepts that are talked about in aerospace structures and statics courses. And so I also recommend going back and reviewing some notes from that to get a more intuitive understanding of how these forces are transferred through components. Next up, the major forces you guys will need to consider. You can kind of split these up between instantaneous and sustained forces. Um, Instantaneous forces will tend to be considerably higher. Uh, the largest, probably the largest force your rocket will experience is recovery forces. And that being instantaneous force applied by the parachute um, onto your shock cord and then into your bulkhead, and then from there into your airframe. And that, I think, is out of the rocket failures I've seen, the most out of failures that were mechanically, most of them I've seen have been due to some failure in handling the recovery forces. For example, the very first USLI rocket, it was built with a bulkhead that wasn't strong enough and it ripped out. It's really important to make sure that not only is your shock cord securely attached to a U or I bolt that is very firmly attached to a bulkhead, that bulkhead also needs to be secured inside the airframe such that it's not going to break out. Continuing on, the other obvious major one is thrust, which is a sustained force, and that's applied from the motor to the fin can. It's important to be able to, since that is, it being a rocket, obviously thrust is a very important force, and it needs to be well dissipated into your airframe. Next up are aero forces, another sustained force that's applied via the external surfaces and eventually onto the internal structure. Motor ejection force, this kind of overlaps with the recovery force sometimes, although it can also be caused by a motor ejection charge if your motor has one. That is, if it's not plugged. And essentially that's any force that gets applied onto the motor, pushing it out. Now that we've kind of covered that, we can talk a bit more about materials. And I'm going to kind of go through some of the different major components and what type of materials are frequently used. Airframe materials to start off with. I talked about this a bit with the L1 guide, but to go a bit more in depth, I've listed what I believe are the most common materials right here. There's certainly some others if you want to do some research, but kind of going from weakest to strongest, we have phenolic, which essentially it's cardboard with epoxy to make a composite. And it can tend to be a bit brittle, and I think it might be a little bit difficult to design with this, but if you keep your recovery forces low, you use a large enough parachute and get a low enough ground descent velocity, you can probably be fine. I wouldn't, yeah, we'll talk about epoxy later. Next up, cardboard, which seems like it should be lower on the list, but the reason I placed cardboard here is because you can buy basically really thick cardboard, which is, it has different diameters than some other rocket components, so you have to be careful with, it tends to be the outer diameter though, you have to be careful with the diameter. It is quite cheap and has decent performance, and in addition, unlike phenolic, it's not brittle, and that will make your failure modes a little bit less catastrophic. You can see in the top right, I have a picture stolen from Lock Precision's website. I recommend checking out their cardboard airframes. My L2 is built with it, and it's, aside from some other problems, it flew quite well with that. Next up, blue tube. Blue tube, I think, is a the actual makeup of blue tube is proprietary, and there's some speculation, but you can look that up if you're curious. Essentially, it's a bit tougher. It's still, yeah. I think blue tube for most rocketry situations in this L2 range, you can kind of just use blue tube and get done with. It is around double the price of cardboard, so if you're looking to save money, it may not be the best choice, but it can work pretty well. Prior to like last year, almost all our rockets were blue tube. It's very easy to work in your system. Next up, fiberglass. You can get straight fiberglass airframes, and those can get a little bit pricey, but those are pretty strong. If you are making something that's going much faster, um, or you're wanting to descend much quicker, the extra strength can be very useful. I would also keep in mind one of the things you can do is you can fiberglass other materials, and that essentially means putting a layer or multiple layers in some situations of fiberglass over another type of tube and epoxying it on to create kind of a composite. And that doing that can help make some other materials, for example, cardboard, phenolic, and blue tube, stronger and have more desirable characteristics. And it can be a pretty, in some situations, pretty cost-effective way to get kind of a middle ground material that's stronger. Finally, carbon fiber. If your L2 rocket needs carbon fiber in order to not break, you've probably done something wrong, or you're probably designing a rocket that is probably a lot more powerful than you really need to get an L2 on. Nonetheless, it is very strong, and you probably can't afford it. One last thing I realized I forgot to mention with the fiberglass. You'll notice in the bottom right picture, there's a picture of a fiberglass sock. If you go and look up rocketry fiberglass socks, you can find stuff like this where it's basically a tube that you can fit your entire rocket tube in, and it makes it very easy to fiberglass your rocket as opposed to having to manually apply a layer of fiberglass, which can get quite difficult. Moving on, bulkheads and fin materials. I think, in L1 territory, you can get away with quarter-inch plywood in almost any situation. In the L2 area, quarter-inch can work fine, but you need to be conscious of the size of your rocket and the recovery forces, because this is the area where you start reaching the upper limits of quarter-inch. I think if you're designing one of the smaller L2 rockets, you can probably get away with it. But if you're going for a larger one, I would consider switching to half-inch. One other thing, if you don't want to buy a separate sheet of half-inch plywood, you can always epoxy 2 quarter-inch things together and make a sandwich. That's something we've done before. Next up, and these I do kind of want to mention. You probably should stick with the wood when you're doing your first L2 rocket, but for larger L2 rockets, go higher, faster, whatever, you may want to consider switching to aluminum bulkhead, which, granted, that requires some machining and that can get quite expensive and heavy. But the upside is it's very strong, and you'll be very hard pressed to actually break it. And you can also, fin-wise, I would probably advise against doing carbon fiber bulkheads, but you could do carbon fiber fins using foam core, basically foam with carbon fiber on the outer edges, and that can make a very strong and lightweight fin. That was used on Yugoslavia's rocket this year to great effect. And there's also solid carbon fiber, which I very highly recommend paying off your student loans first before buying. It is also, in almost any circumstance, very overkill. You can literally, they'll survive free fall. You probably don't need that. And lastly, for either fins or bulkheads, 3D printed materials, which I will very strongly caution you against. You should not 3D print bulkheads or fins or things that need to take significant structural load unless you can carefully plan out how this part is getting printed and what material, along with ensuring that you can actually test it on the ground to make sure that it won't break in flight. I know, speaking from experience, I made the mistake of having a 3D printed bulkhead on my nose cone for my L2, and that was the reason that I lost the entire upper half of my nose cone. So, moral of the story, don't 3D print bulkheads unless you have like very thorough tests. Lastly, some fixturing methods. The main two being epoxy and bolts. Bolts can be a lot of fun and look very fancy. They're very quick to assemble. You're able to disassemble it, which could be advantageous if you want to replace parts, or if something breaks, you could just take the rocket apart and replace something. The downsides being, though, in this case, you then now need to design your parts with threads, which can be difficult. In some situations, you may require getting a tap for metal parts or using threaded inserts for 3D printed parts. And they also will concentrate stress because now you have your, for example, I have a bulkhead and it has 4 bolt points. Instead of the stress being evenly distributed around the entire circumference of the bulkhead, it's now concentrated at the points where the bolts are holding it on. And that's something you need to keep in mind when you're comparing the bulkhead to the actual airframe it's in. You need to make sure the airframe isn't going to get broken by all the stress concentrated where the bolts are. As for epoxy does require some measure of skill in assembly. If you want it to look really good, you have to take a moment and actually do it right. I very highly recommend going online and look up some tutorials about this. Look at what a good example of epoxy job is. Unlike bolts, once you epoxy something, that's it. You're done. You have to break it if you want to disassemble it. But the advantages, there are very few special design considerations. You don't need any fancy tools to do it. And you can be a lot more free with what types of materials you're using. For example, if you're using a wooden bulkhead, it might be kind of difficult to bolt that into the airframe, whereas that's pretty easy to epoxy in. And lastly, if you do it well, you will disperse stress much more evenly. And that can, significantly reduce the loads that particular areas of a part need to handle. To talk a little bit more on epoxy, just real quickly, wear PPE, nitrile gloves. Just don't get epoxy on your hands. It's not fun. But you can also, for epoxy, there's no just epoxy. There's a lot of different types of epoxies that are best for different materials, best for different environmental conditions, and also with viscosities ranging from everything from a light syrup all the way to putty and even clay. And it's definitely important to consider what you're epoxying. If you're doing something like laying up carbon fiber or fiberglass and you want to make a composite with it, you may want something a little less viscous. But in the case where you're epoxying in bulkheads or fins, you may want something more viscous and might even consider using something like putty or clay. And that will make it significantly easier to work with when your epoxy isn't just running off of what you're trying to do. One of the things you can use is also there are some fillers for epoxy, such as Kevlar pulp and that will help reduce the runniness of it, and can create some neat composites. Importantly, though, do your best to create proper fillets. You can see on the left, there's a nice picture from Google of a very nicely filleted fins. Notice how there's a nice curvature to the epoxy, as opposed to on the right is the original USLI rocket. You can see we used Kevlar pulp, which that's great and all, but you can see we didn't even try to fillet it because at the time we didn't know any better. But you can see that it does not look very well. And that will also, if you have fillets really are optimal for dispersing the stress, whereas what we had was and more than that, your rocket will just look nicer. I know from talking with people online, there's several other teams that know us as the team with the expanding foam. But yeah, continuing on, now we're going to talk a bit more about actual structures within your rocket. And so I'm going to go through some of the common structures that you will need to have. And this could vary depending on how you build your rocket, the setup and whatnot, but these will cover most situations. Afterwards, we're going to go into Solidworks and look at some examples. Bulkheads, I've referenced these a lot so far, but the important thing to think of when you're adding a bulkhead is that its primary job is to take recovery forces and disperse them through itself and into the airframe without breaking. And these are probably one of the most critical components when you're thinking about how forces are distributed. You really need to make sure that there's any place where stress is concentrated on your bulkhead, that your bulkhead can withstand it. Because if you break a bulkhead, all of a sudden you have a free-falling object, and that's no good. It's really important to look at how your bulkhead is fixed to things. As earlier, I just referenced the epoxy and bolts. If you use bolts to affix your bulkhead, you need to make sure that both the airframe and the bulkhead itself can handle that. You'll also need to make sure that it can handle just the forces of the actual harness on it. Because of the nature of U-bolts and I-bolts, those will tend to concentrate force in the center where you mount them. It's a very important part to get right. Fin cans. So fin cans kind of do a lot of things, basically just the bottom of your rocket. It needs to hold the fins and the motor in the correct orientation without any movement. You should strive to reduce vibrations and play, because if stuff is moving around, then all of a sudden your rocket, you introduce various moments and your rocket will have an unstable flight. Safety wise, it is critical that your fin shoulder should extend to the motor tube. Basically, shoulder being the tab on the fin that goes on the inside of the rocket. That is one of the things that could show up on your NAR level 2 exam. It's all about fin shoulders. Also, you need to make sure that you're using centering rings well, and those will do a good job of dispersing the force from the motor onto the actual airframe. So you'll usually want several of them, not only for that, but also to ensure, as the name implies, that your motor remains centrally located and that it's not canted. And finally, if you recall the motor ejection force, make sure that you have something to prevent your motor from coming out. There are many different ways to do this. everything from just clips to like retention rings. Lastly, I want to talk a bit about electronics bay, since this is probably the easiest one to mess up. Usually, in most situations, both sides of your electronics bay must take recovery forces, usually at least one side. I will say if you only have one side, then you're probably, both sides is probably an easier design rocket-wise. But in any case, it's important to consider how your electronics will be mounted. And this is vital to ensure that all your electronics are static in place and not bouncing around the inside. Typically for most altimeters, they'll just have holes in them that make it easy to put a screw in them and mount them directly to a sled or some sort of 3D printed mount. If you're able to design one of those, that could be a very convenient thing to do. But you also have to keep in mind components like batteries and whatnot that don't just have a convenient mounting hole. You need to make something to keep them in place. You also need to make sure that your rocket is actually sealed off from the electronics bay. One failure mode that you want to avoid is having ejection gases leak from a black powder charge just above the E-bay. You want to avoid those leaking into the E-bay, because that will increase the pressure and could cause your rocket to think it's at some other altitude, possibly even causing another charge to deploy, which will mess up your day and your rocket will drift very far. Finally, remember to, I guess not finally, I have one more point after this. Remember to add holes for arming switches and pressure balance. If you don't have any holes that go to the outside, your rocket won't be able to tell what pressure it's at. And then it can't work. Lastly, please consider ease of setup. You very much want to minimize field setup time. If your eBay takes like 1 or 2 hours to assemble at the field, then you're going to miss launches. Yeah. So moving on to some examples, we're going to go into Solidworks now and take a look at this right here. There's a few parts in, but this is a very basic fin can. And you can see there's the fins, tube for the motor, and centering rings. And this is really the basics. And you'd have, your actual airframe tube that slides down around the outside. Unfortunately, I don't have one catted, so I can't put that in. But essentially, you'd assemble this section, put it in, and whatnot. This could very easily be assembled using epoxy by filleting all these different interfaces, putting a fillet right there, etc., to make sure that it's all well and good. I will note this does have 5 fins. The easiest way to assemble a rocket is using 4 fins. That makes it really easy to make a jig to keep the fins properly angled and not canted when you're assembling it. That is one thing. If you're assembling with epoxy, you will need to be sure to hold everything in place while the epoxy cures. And you can see one thing missing from this is actual motor retention. And so in an actual design, you may want to drill some holes and add some clips here. This is probably one of the simplest ways you can design it. Now, if we unhide some components, you'll see this is actually more complicated than you initially thought. Now this right here is the the fin can for my rocket, for my L2. And you can see here, instead of just having the fins epoxied straight in, now they are located within this 3D printed mount. And one thing that you could do, you could epoxy them into a 3D printed mount and onto, you know, the other parts and call it a day, and that will probably reduce the difficulty of assembly. We'd see I've kind of mixed epoxy and bolts by having most of this be epoxy together, and the fins are bolted in through these slots. And this is advantageous because, you know, fins are probably one of the parts on your rocket you're most likely to break. And so if you're able to replace fins, that could be really helpful. I know I didn't really break a fin, but I definitely very much scuffed up a fin that I'm considering replacing, which I can do because I can just take the fin out. And so it's changes like these you might find will make your standard fin design a little bit easier to manage. Yeah. So now we're going to take a look at the USLI rocket to kind of see very fancy fin can design. Once this cross section gets done, I probably should have done this beforehand. My apologies. In the meantime, I definitely very highly recommend making a CAD model of your rocket before you actually build it. That way you know for certain where all the pieces are and how you're actually building it. You by no means need to like build it, you know, perfectly to the CAD model, but it really does help. So you can see in here, I'm actually gonna hide. Dang. Okay. I'm gonna hide the lower airframe, so I'll be able to get a better look. So from here, you can see the USLI design. We have rather than centering rings, brackets on either the top or bottom of the fins, and then this is completely assembled with bolts. And obviously something like this takes a lot more work to design, and is probably more than you will want for your L2. But it can be useful to see how some of these patterns look, and how you could possibly translate some of these concepts into your design. You'll notice one of the things I know I caution about using 3D printed components, whereas these brackets are 3D printed. So in a situation like this, where you really do want to use some 3D printed components, because they're an internal structure, and they that makes it a little bit easier. They're not bulkheads, which is nice. And in addition, it's also printed out of nylon X, which is carbon fiber and nylon. So it's a very strong material. I would if you are considering doing anything like that, use something that's reasonably strong. Don't use PLA. If PLA gets too hot, its strength goes out the window. And especially where this is right next to the motor, that's not a good time. But yeah. You'll also notice that for retention, as opposed to the clip design I was talking about earlier, there's a full-on threaded bolted on ring system down here. And that can get a little fancier. You can actually go on and there are boat tail retention systems online that you can buy that I would also suggest looking into. And then the other parts I want to show you was the kind of two types of eBays you could do. And not two types, two examples of eBays. So here we have my L2 rocket, which is, this is the very simple, straightforward type of eBay design. This type of design is much more like classical, and you'll see it a lot online. But the idea is you essentially have outer frame, and if we, a quick note before I hide this, you'll note I have a lot of detail on this. This is because this is a 3D printed component. I've since learned that this probably wasn't the best idea, but this did the job. You can easily do the same thing by having one thing of inner tube with a small ring of outer tube right here. So now if we hide this, you can see the interior structure of the eBay, which granted this design is a little bit odd since typically you'd have a vertical sled. But in this design, you can see I have this mount on the bottom, which holds a 9-volt battery for power, and this mount right here where the electronics get mounted. And because it's a level 2 rocket, it's not for any competition or anything. I only have one strato, and that makes the wiring very simple. It just needs a pressure hole, and it needs to be connected to the charges and the battery and an arming switch, which is all very straightforward. It's not in this model, but I would have some holes that the actual charges go through, and I very highly recommend putting the wires through and then using epoxy or something else to seal it, and then you could put some kind of screw connector on the other side, and that'll be an easy way to mount charges. The downside to a type of eBay like this is very easy to make all the parts for, and it's very simple. Oh, I realized I also forgot to mention that these cylinders are threaded rods that I was too lazy to fully CAD myself. The idea being each of these parts is held in place on the threaded rod using nuts that secure it in place. And this has the advantage of, in this case, the threaded rod is the thing that takes pretty much the most of the force. And that was, what keeps the force off that 3D printed component that I had for the exterior. And also not shown, but, there'd be a U-bolt or I-bolt in here. The big downside to something like this is that it takes really long to assemble. Having to get you're trying to work with parts that all need to go in the same space, while also trying to get wiring in there, connections. You need to more or less make really long wires, assemble it all outside, and slide it in, and it can become a mess. It takes forever. You do not ever want to do that at a launch field. If you're having to mess around with a sled type eBay at a launch field, you're going to have a terrible day, especially if it's like winter. It's no fun at all. You absolutely need to make sure that you can assemble it beforehand while you're in the building, and not on launch day, in such a way that you have the wires coming out of it in order to connect to the charges. And even like I'm really dreading having to reassemble mine because I took mine apart to get data off the altimeter, and I'm not looking forward to putting it back together. But I'll say, if you just need this to work for a flight every once in a while, it's not something that you need to worry about taking apart really quick, you don't need data off it that often, this is a fine design. And it does really work for, a first one. But I would say you could probably, if you're creative, find a way to make this more usable. And finally, we're going to take a brief look at the eBay for the USLI rocket to see kind of the very polar opposite. So you can see in the USLI design, there's a, on either side, it's hidden down here for some reason, but there's an aluminum bulkhead, which is necessary because of the higher forces this rocket experiences. It flies higher, falls faster. And rather than having a threaded rod to transfer force, there's a nice sturdy aluminum bar. And something like this is very, very structurally sound, and you'll be hard pressed to break it. Again, that's something that is probably pretty difficult to do for your own L2 just on your own. But you may want to consider adding something similar. Just off the top of my head, if you really needed some extra force, you could probably find some way to do it with like, a bar that you can buy at Home Depot or something, or a pipe. I don't know. Be creative. But you'll also notice, rather than having a sled, there's a 3D printed mount that has specific, you'll notice it has mounting holes for every electrical component. And that makes it very organized. I believe this also has very simple wire routing, or not simple, planned, I should say, as opposed to my eBay, which is more or less just get the wires long enough and shove it all in there. And this can be very appealing. And lastly, because I won't go into the details of the mechanism. I'm sure you could reach out and talk to someone if you're curious about it. But this eBay, to install it, it gets inserted, twists, you put in a few bolts, and it's done. Essentially, the bar down here locks into plate. And that, that's the more or less the complete opposite of what I had, whereas the simple sled eBay can take like an hour. This takes like a minute. I definitely think it's worth putting a bit of effort and considering how your eBay is assembled. I know it wasn't a regional plan out, but I think I will show you some of the other eBay designs I made a while ago. I will caution you that these were never actually used. But just to give you some examples of ways you can be creative, we have, I'm going to close this so that Solidworks doesn't get angry. Don't save. Give that a moment. There we go. Here's probably the most wild eBay I've designed. So you can, if we look at this, you'll notice that there's a lot going on with this eBay. This was this was designed essentially for my L2, but I never ended up using it. But the idea being with this, you have a hinge, so that rather than opening the eBay from by taking the bulkheads on or off, it hinges open. And you'll notice, this was intended to be 3D printed. You'll notice that I have 3D printed bulkheads. This was before I learned that that was a terrible idea. Don't do this. And there's holes to have one threaded rod that goes through the hole through the center. And you can see, I have mounting points for the altimeter and a battery and a switch and like this hole. I know this original plan also involved putting a Raspberry Pi with a LiPo battery. And there's also this camera hood right here. This probably could have been done with a much simpler system, but it was interesting to CAD. So you can see you can get pretty creative. And lastly, as a sort of middle ground, I have a weird triangle eBay if I can find it in this folder. I have too many eBay parts in this folder. I'm sorry. Here we go. So this one is kind of a mix between some of the other things, but you can see if I scroll out, you can see that essentially there's a sled in this that is on this triangle 3D printed sled where you have, you'd have your electronics mounted there and a battery and whatnot. But this was me trying to make a sled that was easy to put in and take out. And you'll notice I had to do some weird things like inset this is the arming switch right here. Once it's in, you have to reach in quite far with a screwdriver to get at it. Not ideal, but it works. And you can see this also does retain the non 3D printed bulkheads along with threaded rods. And I believe there's actually a spot for a third threaded rod here. I don't know why there's a threaded rod there, but so yeah. I would encourage you to put some thought into how your eBay gets assembled. With that, does anybody have any questions before I stop recording?
Nope.
Cool. I will stop recording.